If you've been watching my channel, then you'll know that most of my videos are about vintage electronics, vintage computer systems, vintage mechanical machines, but that's mostly my personal hobby. It's not something I make money doing. My actual career started in optics. I was an optical specialist for several decades, and the type of equipment I used to work with was something like this. If you've never seen one of these, this is a scanning UV vis spectrophotometer. This particular model is a UV1201 made by a company called Shimadzu. I never worked for this company. I worked for a UK company that designed, developed and manufactured very similar types of equipment. I actually rescued this machine from a skip about 25 years ago. It was non-working. I went through it and repaired it, got it all up and running. As I say, it's a UV vis machine, so it has both visible light and UV light sources. If you are interested in this type of thing, or if you're interested in optics, then let me know and I'll post some videos on using this. I will quickly go through what it is and how it works in this video. But the reason I'm making this video is I came in to do some experiments this morning. I switched it on, it started going through its self-test, and then there was a loud bang, cloud of smoke, and I quickly turned it off. Judging by the noise and the smell, I think capacitors failed in it, so I thought it would be a good opportunity to make a video. So as I say, I'll explain what all this is later on, and then if you're interested I'll post some more videos showing some experiments with it. But essentially what this does is it shines light energy of different wavelengths through a sample that you place in the sample chamber. It measures the amount of light that's absorbed by the sample, and it plots the result as a graph, and then you can work out what is in the sample. But as I say, this needs repairing now, so I'll get the cover off, we'll have a look inside and see if we can figure out what's failed. Okay, I've taken the outer cover off, and although you probably can't see this, there's a mains input connector down here with a filter on it. And one of the things I've always said with these old machines, especially vintage computers, is these are a notorious failure point. And although it's probably not really visible, there is a brown dirty spray mark that's surrounding what appears to be a blowout in the back end of this filter, so I suspect it's this filter that's failed, and it is quite common. Another reason I think it's probably that is the smell. These smell really bad when they fail, and that's what I'm smelling. The entire lab smells of failed input filter, and it has a very distinctive smell. So I suspect that's what's failed. What we've got in here, if you're interested, and let me know if you are interested in these, and I'll go through this in a lot more detail, but we've got a multiple optical source. So I'll just move the camera so you can see in. This is kind of where the light energy is generated. So I'll just move the camera around so you can see into that. Okay, so what we have here is a tungsten lamp. It's quite high intensity tungsten lamp, and because of the amount of energy that we need to get through this, the way these systems are organized is the filament within the tungsten lamp is actually focused into the collimator. So there's a mirror here. This is a rotating mirror, and depending on which of the two light sources is required, the motor at the bottom here rotates and it tilts this mirror, and in the location where it's reflecting the tungsten light source, the filament of the light source is focused onto a vertical slit. So it comes across here, hits the mirror, is reflected, and it goes into the optics through a slit down here which you can't see. If we want to use the UV light source, that's this lamp here, so the deuterium lamp, and the mirror will then rotate to focus the energy coming out of the aperture in this lamp, reflects off the mirror, and goes into the optics. All the optics, any lenses, etc., are not glass, because glass will of course absorb the UV, so they're made of silica, all very expensive, and these lamps are about £1,000 each, so it's one of these things where you're always hoping that the lamp's going to actually strike when you turn the machine on, because it's quite an expensive exercise to replace them. Also, you have to realign the optics when you do that, so luckily they do last a long time, but ultimately they will fail. But as I say, the next step is to get the mains filter changed. So once the light comes through and goes into the optics, let's move the camera across. It goes into this enclosure, and this is enclosed of course to keep stray light out, and the light comes into here and it's split into two paths, and one of those paths goes onto an optical grating, so it's a holographic grating, and that performs a very similar function, or the same function, as a prism. It splits the light into a rainbow, and the grating can be rotated, and in fact when the unit scans, that's how it scans, it rotates the grating, and depending on the angle of the grating it will shine a wavelength of light that's specific to that particular angle through the rest of the optics, through the sample, and then there's a detector on the back end of the optical path. So it's not really measuring the colour of light, it's just measuring the energy at different wavelengths, and it plots that as a graph. And there's a second channel that it uses as a reference channel, so it's got kind of a black level clamp to reference, because these do read to very precise energy levels. But as I say, that's a very brief overview. If you want to know more about this, then let me know and I'll go through this entire thing in far more detail. But what I'll do now is get this filter out of the way and see if we can get the machine to come back to life. Okay, well luckily it has got a separate main switch. It's not all integrated into one unit, so it may be easier to deal with than I thought. In fact, what I'm going to do, because this is still a fairly unusual looking unit, this is what I was talking about when I think the unit's blown. I will test the unit and apply some power to it. I've tested the rails already. There doesn't appear to be any shorts on the actual power rails, and also I can see from this that it has blown out through here, and it's fairly recent. It's still very sticky and there's a lot of residue on the back of this plate. What I can probably do with this is pop this cover off and just take the guts out of this, and then there is space behind here for a standalone filter. So what I'll probably do is empty this out, take all the failed components out of it if this is indeed what's failed, and then what I can do is just bypass this, so it's just a straight through connection, and then put a separate filter in. So I'll get this out of the way, I'll get this opened up and we'll take a look inside. Okay, well it put up a brave fight, but I finally managed to get it depotted. Of course what's in here is a couple of capacitors and an inductor, and then the whole thing's potted, so I had to peel off the outer metal, pick out all the potting compound, remove the failed parts. Both capacitors had failed, and as I said, they'd blown some of their contents out onto the back of this. So on the back of here there's a lot of gunk I need to clean off. Smells foul, the whole lab really stinks at the moment. But what I can do now is just connect these points directly to the pins on the socket. At some point I may just find a small mains filter to put between these 2 points, but for now I'll just join these directly together, and then I can reassemble it and see if it still works. Okay, so I've just put some shorting links in for now, reattached the earth lead, and what I should do is put a filter in place of these links. My bench does have a filter on the incoming supply, so I may never get around to doing it, but that's really what I should do. But I just want to see at the moment if it works and if there are any other faults I need to fix before I can use this machine. Okay, that's the socket and switch refitted and reconnected, and what I can do now is put the outer cover on, power it up and see if it works. Okay, I've got it reassembled. I've refitted the cell changer. This device, by the way, just allows the machine to select different samples automatically, and then it can do a sweep on each of the samples and compare them, or just run multiple samples in one program. What I'll do now is power it up, see if it works, and hopefully it will come back to life without any smoke or noise. So I'll just move the camera so you can see the screen. We'll power it up. The self-test does take quite a long time, so I'll probably fast forward through this, but what it's doing is it's checking that the monochromator can successfully calibrate itself, and also that the two light sources have sufficient energy output across the entire wavelength range that the machine can support. So it does take a few minutes, but I'll fast forward through it, and then hopefully it will pass all the self-tests. As I say, it was just a complete failure earlier on. It just blew a lot of smoke out the back, but I'm fairly certain that was just the filter. Okay, so that's a good sign. So we'll just wait for the self-test to complete, and then I'll just demonstrate it doing a quick run so you can see what it does. Okay, so it passed the self-test, so that's looking quite promising, and what we'll do now is a very quick run just to demonstrate what the machine does. As I said, if you want more videos on using a machine like this, then let me know. They're extremely versatile, very interesting once you get into optics and what you can do with them. But essentially what the machine does is it shines light through a cuvette like this, and depending on what's in the cuvette, it will absorb different waves, different wavelengths of light by varying amounts, and the profile you end up with will allow you to determine a lot about the sample. So you put your sample into one of these, this goes into the cell changer, and then you program the machine to sweep through a certain range of wavelengths, and it will measure the absorption or transmission of light at each of those steps. Before we can do that, we need to do what's called baseline correction. So because we're sweeping over a very wide range of frequencies or wavelengths, this machine is very capable. It will go from 200 nanometers, which is well into UV, up to 1100 nanometers, which is practically into the infrared range. So it's got a very wide range of operation. It has two light sources. One's a tungsten lamp and one's a deuterium lamp, and of course the energy levels as you sweep across the frequency range varies, and so because we don't want that superimposed on our readings, the machine does what's called a baseline correction. So it will step to each of the wavelengths that the machine is capable of going to. So it will move in small steps to each wavelength, it will take a reading, and it will use that reading to auto zero at that wavelength, and then when we do an actual scan, it will use that saved baseline to correct the readings it's taking from the samples. In other words, it removes the background variation in energies, and for example, if we then did a scan with nothing in the cell changer, we should get a flat line. So we can be sure then that anything that we see in terms of data coming out of the machine is because of the sample, not because of the differences in energy output of the lamps at different frequencies. Because I don't want to sweep over the entire range, what I'm going to do is select a range of operation. I'll restrict it to a much narrower range to save a lot of time. The range you use, of course, depends on what you're looking for. but the first thing I want to do is set the two wavelengths it's going to scan between. So we'll scan between 600 and 400. And now it's going to drive to 600 because that's the starting wavelength. Okay, and also I'm going to increase the scan speed. The faster it scans, the less accurate, and of course the slower it scans, the more accurate, but it takes far longer to do the scan. It can take an hour or more to do a full scan at slow speed, so I'll speed that up and we'll go to fast. And now we'll do a baseline correction. This will take a few minutes, so I'll fast forward through this, but it's just, as I say, auto zeroing at all the points over the range that we've selected. Okay, so it's corrected for the baseline. Notice we also have this measurement mode at the top, and if I select that, it's gone to, it says T%, that's percentage of transmission, so 100% is all the light's getting through, and as that energy level drops, then the percentage drops, and obviously 0 is when no light at all is getting through. Absorption is the inverse of that, so it's a log scale. 0 absorption means all the light's getting through. If only 10% of the light was getting through, it would be a absorption of 1. If 1% was getting through, that would be an absorption of 2, etc. So you can see that we're going down here to 1,000th of absorption. So in other words, it's an extremely precise machine. It can detect incredibly small changes in the level of light. So what we'll do now is we'll do a scan. You can see what happens if we scan it with nothing in the cell changer, and then we'll do a scan with something actually in the light path. So we'll get this started, and it's running at a fast rate, so it'll be fairly imprecise, but you'll see the sort of thing that we'll get. Starting at the 600 nanometer point, of course. There will be noise on this. It's only been on for probably 20 minutes now, and it does need to be on for a few hours to get the most, but you can see that the scale here is plus or minus 0.01A. In other words, this is a very small change in light levels that we're looking at, so it's looking at light levels in a very precise way. So 400 nanometers to 600 is kind of the middle of the visible range. That's the light levels or light wavelengths you'd normally see, what we normally call colours. But this machine will go well beyond what's actually visible, and that's why it's called a UV vis spectrophotometer. It goes from UV light, which we can't see, through the visible range, but it also goes well beyond the visible range towards infrared that we also can't see. We generally sense that as heat. So you can see the baseline correction's been fairly good. It is auto ranging this, so this is a very small error we're looking at. It would be a lot smaller if we allowed the machine to warm up, and also if we allowed it to run more slowly, and it will do peak detection. Normally I use this machine connected to software for proper analytical purposes, but this is just a quick demonstration, so I won't do that. And what I'll do now is put a cuvette in the light path. So all that's in that cuvette is distilled water, but you will see the difference it makes when we do a scan. So I'll start that now. It's going to run over the same range of frequencies. Okay, so you can see it's done a scan, and what we have here is an indication of how distilled water will look over this wavelength, this range of wavelengths. What's happening here is it's fairly flat down to about 450 nanometers, and then the absorption starts to rise fairly steeply, and that's because water starts to absorb UV at the lower wavelengths. So if we carry on going down to UV, it would go up quite steeply, and that's why you don't get sunburnt underwater. And so, as you can see, what the machine's used for is to examine samples, and what you'd end up with normally is a fairly distinctive set of peaks depending on what the materials are that are in the sample. And that's what it's used for. It's an analytical machine. It's used to test samples, see what's in them, how much of different substances are in there, and they're used extensively in research and medicine, and that's mainly where I use these. So if you are interested in seeing more videos on this machine, then let me know, or I'll set up some experiments and we can do various tests with it to look at various materials. And the other sorts of things you can do with this is, for example, looking at things like sunglasses and seeing just how ineffective certain cheap sunglasses can be. As I think optics is one of those things that's fairly misunderstood, and I think people think that a set of dark glasses is good for your eyes, and that's not necessarily the case. If they're not blocking UV, then they're fairly useless. And a lot of cheap plastic sunglasses don't block UV at all. They're just tinted plastic, which still lets the harmful UV through to your eyes. And a machine like this is very good for examining plastics and liquids and substances to see exactly what their performance is over a wide range of wavelengths, but also to look at the materials themselves and see what they consist of. Before I finish this video, I'll actually run another sample. This is the sample I was intending to run before the machine failed this morning, and I thought I may as well show you the results, but it will be running over the full range that the machine can work over. So it's going to run from 200 up to 1100 nanometers, so I need to run a full baseline and then the scan. I won't bother videoing that, it'll be fairly tedious to watch, but I'll show you the results once that's finished. Okay, the scan is complete. I will point out here that I did the baseline correction with an empty cuvette installed, so that gives me a more precise result, because obviously it takes into account any changes that the cuvettes themselves introduce. So it is important to use matched cuvettes to make sure that they give as much of a like for like as possible, and so it's giving you results based purely on the sample and not on the instrument or the cuvettes themselves. So did the baseline correction. You can see I've now done the scan. It's this peak here I'm actually interested in, and what we can do is look to see what wavelength the peak is at. So in this case it's at 974 nanometers, which is just to confirm it's the peak that I was interested in. And what I can do now is zoom in to give me a bit more resolution in that area. So I can zoom in and select the range we are examining the signal over. So if I say 0.25 absorption and down to minus 0.1, and I want to look at this from about 700 nanometers up to 1100, and that will allow us to zoom into the signal, and we can do a more precise peak measurement now that we've zoomed in. And sure enough, it's at 974, and I can also see the level of the signal. So the absorption level is 0.187. Now this is a comparative test. I'm comparing against some other samples that I have, and I'm looking at something in particular. There's some misinformation going around at the moment I'm just looking into, and this is the purpose of this machine. It gives the ability to look at samples and substances in a great deal of detail. You do need reference curves, of course, or if you're looking at a reaction rate, for example, again you can use this machine to do that. If you're interested in this machine, as I say, let me know and I'll do a few more experiments with it and explain more fully how it works. But this was really just a repair video, and luckily it was a fairly simple fault to fix.